Hello, my name is Navid Zuberi. I'm an assistant professor at the University of Washington, Material Science Engineering Department. And I'm presenting this work on behalf of myself and my co-author, Professor Anush Pursartip from University of British Columbia, who is also with Convergent Manufacturing Technologies, a company located in Vancouver, Canada. And the work is on applications of machine learning for process modeling of composites. If you look at science-based simulation versus data-driven modeling in general, as we call it, machine learning these days, think about a specific physical problem. Let's say heat transfer during processing of composites. To solve this problem, traditionally, we start with understanding the underlying physics, establishing partial differential equations that describe that physics on the basis of conservations, usually conservation of energy or mass or momentum. We characterize the problem, and then we set to solve the problem numerically using methods such as finite element methods. That's a very well-established method with rigorous mathematical foundation. With the recent rise of machine learning, we have now a new approach, which is a theory-agnostic approach based on data, and seemingly it doesn't need any domain knowledge or physical understanding of the problem. It starts with data, and you do a data fitting exercise. You fit these very sophisticated neural networks to the response that you have by basically adjusting the constant of the neural network. So it's a data fitting exercise, but it's a very complex approach for data fitting, and it needs data. So let's compare these two methods, finite element methods versus machine learning. Each of them has its own advantages, and each of them has its own weaknesses. If you look at finite element methods, starting point for it is that you have to have those partial differential equations. You have to have your material properties, your boundary conditions, your initial conditions for your entire process, and then you can solve the problem. Without those, you cannot solve the problem. There is always trade-off between fidelity and speed and cost, basically. And fidelity here has nothing to do with accuracy. But as you make your model more complex and to capture more physical aspects of the problem, it becomes slower. It becomes also more difficult to characterize. It becomes more expensive. These finite element models usually have difficulties tackling uncertainties. For example, unknown boundary condition, which is a very common thing in manufacturing process, they have difficulties addressing that. Comparison of that, machine learning, you need a lot of data. Where does the data come from? How many data points do I need? And I'll try to answer those questions here. Once they're trained well, they are extremely fast to the point that they can be considered near real time. Unlike finite element, it takes time to solve a problem. They just need a lot of effort upfront, and they are basically instantaneously can give you the answer. They're also usually inaccurate outside of the training zone, and that's something that I'll come back to this later. If you look at the source of data, where does the data come from? Of course, you have the entire factory. If you think about the chain of how the material goes through what's the process the material goes through the factory. You have material deposition, AFP, you might have processing, autoclave, you might have co-bonding, co-curing, thermoset or thermoplastic. You have machining, NDI, repair. Each of these processes generates tons of data, thermocouples, strain gauges, NDI result, ultrasonic results in terms of images, or just actual numbers coming from NDI. Each of these can be used for training of a machine learning model. What else do we have in terms of sources of data? Data might come from test and simulation as well. When you're characterizing material, when you're characterizing process, you are basically generating data. Where you're going through the entire building block approach and doing hundreds of thousands of tests, you're basically generating tons of data. But data can also come from simulation. You might do failure simulation. You might do process simulation using finite element models. And that seems a bit odd if you have finite element. Why do I need to generate data for machine learning? But you will see in a minute that why that is quite important. So data might come from different sources, and all of these data are available to train or to fit a neural network or other types of machine learning models to the response. So now I'm introducing you this new paradigm, which is called theory-guided machine learning. It basically says we have different data streams. We have physical data, comes from tests or processing of the material. We have visual data, comes from numerical simulations. And we have theories, closed form simulations, our understanding of, for example, if I change one parameter in the problem, what's going to happen to the output. These are all explicit or implicit knowledge, which combined with physical data, combined with virtual data, can be used to train very sophisticated neural network to represent that entire set of data. So again, theory-guided machine learning, or TGML, short for that. If you go back to the processing of composites, it might look like something like this, that you're building a really large, complex part, which is basically, let's say, prepregs are placed on thermally massive tools, heated in an autoclave. Let's say the air temperature is set. It's the blue curve here that you see, which shows the temperature versus time, and you're measuring the part temperature, which is the green curve, thermocouples that you have placed inside the part. And the aim is that part temperature has to be within the bounds such that you're satisfying specs. Once you satisfy the specs, that becomes a satisfactory part that can fly. If that green curve that represents the temperature history of the part is not within the specs, this is not a good part, not a satisfactory part to fly. If you want to solve this problem, for example, setting the air temperature, what is the part temperature? Do I satisfy the specs or not? You have to solve a heat transfer problem. And this is a 3D heat transfer problem. You have your part sitting on a tool. You have the equation that describes it. There is the convective heat transfer. There's heat generation from, for example, exothermic reaction in the part. And you can solve this problem using finite element models. For this specific problem, understanding the physics of the problem away from the edges of the tool, away from the substructure of the tool, you can approximately say this is a 1D problem. The heat just goes through the thickness of the part, through the thickness of the tool. It becomes approximately a 1D problem, which means that instead of looking at the actual complex problem, in some cases, to make it faster, we can just do 1D FE analysis, or as it called it, 1D true thickness drill through, a part sitting on a tool. Let's get that concept and see how far we can go with that. Let's do a case study. Let's say I have a part, this is Hexcel AS48552, with a given thickness, sitting on a tool, in-bar tool, with a given thickness. And there's some airflow around this, it's convective heat transfer. There's some heat transfer coefficients, H1 and H2, that they have a range. And then we set the air temperature. That's the black curve that you see here. And we look at the part temperature. Let's say the center of the part temperature. That's the red curve. And then we're looking at some key performance indicators, KPI. Or we're actually looking at to see if you're satisfying specs or not. In this case, let's say we're looking at exotherm, which is the maximum deviation of the part temperature with respect to air temperature. And then thermal lag, which is how much, what's the maximum lagging temperature compared to the air temperature. And let's say these plus other key performance indicators are basically the specs that we have to check, make sure they're within a bounds to see if we're satisfying the specs or not. Can we train a neural network that gets the inputs of the finite element model, thicknesses, the heat transfer coefficients, the thermal cycle, and give us these key performance indicators, exotherm, thermal lag? Basically replicate what finite element does. And we're going to see in a moment why we need to do that. What's the advantage of doing that? So this is done like this. First step is data generation. You need to generate data. Data generation in this case was done, these are all visual data, using Raven software from Convergent Manufacturing Technologies, where we generated 20,000 data points. And these data points were generated by randomly setting the heat transfer coefficients, randomly setting the thicknesses, and randomly setting our Q cycle. The part was always Hexcel AS48552. The tooling material was either in-bar, aluminum, or composites. From each of these 20,000 simulations, we looked at the values coming from the finite element model, thermal lag, exotherm, minimum part viscosity, or other things that we were interested in. The training was based on these data from theory. And you will see in a moment why that theory addition is quite important. But it's a neural network that gets the inputs of the finite elements, the heat transfer coefficient and thicknesses, in this case, the heating rates, of the Q cycle and tries to predict exotherm. This is a specific neural network. But knowing the problem, we know that the effect of the heating rate on exotherm for this 1D problem is exponential. It increases and then plateaus to a certain value. And beyond the certain heating rate, doesn't matter how fast you're heating up your part, the exotherm doesn't change because it becomes like a fast step up hold cycle. So the part doesn't feel if you go faster beyond the heating rate. As a result, the effect of heating rate on exotherm is exponential. This certain neural network was trained based on that 20,000 data points from simulation, plus this one piece of information, which was given to it in terms of a pre-transform heating rate. So you can tell that we trained a neural network with both virtual data and theory. And you will see why that is extremely important to do that combination in this case. Here I'm showing the result, two results that you can basically understand many of the questions I was asking so far in this presentation. The left curve shows the error, the deviation of this neural network from finite element. So you train the neural network, then you try to do predictions with it, then you compare with finite element, and you see how much error you have. That's the vertical axis. That's the mean error. The horizontal axis is the size of data. We use different size of data to train different neural networks and looks at their error. We wanted to know how much data do we need at the end. As you can see, as you increase the size of data, go from 500 simulation to 1,000 simulation, 2,000 simulation, the error drops, but then becomes constant, which means that beyond certain number of data points, you really don't need data. In this case, it seems that we need 1,000 data points. We didn't need 20,000 data points. We need 1,000 data points to have an effective training of these neural networks. The other two things are the colors. The one that are orange are the neural networks that were only trained based on virtual data. The one that are blue are the one that are trained on both virtual data and also theory. First of all, you can see that in general, they're more accurate than the other models. But perhaps it's not quite obvious here how much accuracy you're getting. You will see the accuracy in the other curve. Just want to point out that once you train this neural network, once they're accurate, the deviation from finite element, as you can see, is below 0.5 degrees CA. They're basically identical to finite element at this point. And again, I'll show you in a second why we are mimicking finite element. If you have finite element, what's the point of creating something that mimics finite elements? If you look at the other curve, it shows the predicted exotherm for a case compared to if you give different heating rates. So imagine you have a thermal stack, heat transfer coefficients and thicknesses, and you're changing the Q cycle for that. Go lower heating rate, higher heating rate. You're really looking at how much exotherm I'm getting. So this is the exponential response I was telling before. The dashed black line is the finite element prediction. It says this is the exotherm you have in the given heating rates. The blue line is the predictions of a neural network which were trained on both visual data and theory. It mimics the finite element perfectly. But here's the catch. All of these neural networks were trained only from the range of the heating rate given in this green zone, which is between 1 to 5 C per minute. They never saw any data beyond that zone. If you take a random neural network, which is just trained on visual data, not the theory, the prediction is very accurate within that green zone, which is the training zone. Outside of that, it breaks down. So here's the conclusion. If you're training a neural network within a zone of data, you can never trust it outside of that zone unless you're training it with theory as well, unless it understands the physics that govern the problem, even outside of that zone. Then it becomes an accurate model. So where do we use this? Now we have a model which is as good as finite element model. When you're basically going through different design phases and you're looking at manufacturability of a composite part, let's say in this case, the composite being a skin. And let's say you are in a conceptual design phase where thicknesses and geometries are not set. So you are trying many different things. You're changing the geometry, you're changing the tool perhaps, and you want to know if you can manufacture it or not. Normally you have to do a 3D finite element analysis, but that takes a long time. There's a commercial tool that can do it faster. And the commercial tool is called CPATA. by Convergent Manufacturing Technologies is a plugin for CATIA. It can assess the manufacturability of a given part, and it does it by dividing it into many 1D zones. And instead of doing full 3D analysis, it does many 1D FE analysis. So it becomes faster. Even that is not fast enough if you're in the conceptual design phase. Something like this for a wing skin might take half an hour. So here's a comparison. And these comparisons are all for different methods, the same part, but we're looking at the speed. And think about it, the accuracy is more or less the same between all of them. In one case, as I mentioned, you can get a complex part sitting on a complex tool, do 3D FEA simulations. You can use commercial tools like Comper software and Abacus. If you want to do the optimization of the thicknesses and the thickness of the part, thickness of the tool, tool material, this might take hours to days to go through this exercise. You can do the same type of analysis using Cipata software in CATIA, where it divides a wing skin into many different zones, 1D zones, and conduct many 1D FE simulations with different configuration, let's say different tool thicknesses and different Q cycles, and tells you if you can manufacture a part or not. That takes 27 minutes in a typical engineering workstation. So you set the part, you set the simulation, it takes half an hour. You have to wait for the simulation to be done. Recently, the model that I developed, the trained model that I mentioned, the theory-guided machine learning models, were implemented by Convergent Manufacturing Technologies. So the Cipata, instead of, it does the 1D, it basically creates 1D zones, but instead of doing 1D FE analysis, this time it relies on the trained neural networks to tell if it can satisfy the specs by looking at the key performance indicators. And something like this for the entire wing skin took 2 seconds on a typical engineering workstation. Think about the revolutionary speed you're gaining. You go from 3D simulation, days, hours, to 1D simulation, being smart about the problem you're solving, half an hour, to rely on machine learning models, you reach 2 seconds speed, real-time FE simulations. And that's a technology that has no parallel at the moment. There is no other way you can replicate that efficiency in the model. And that's one of the biggest appeal about machine learning models, and specifically in this case, theory-guided machine learning. So what are the main key points that I wanted to convey in this presentation? I want to basically emphasize the significance of combining two words, science-based simulation, data-driven modeling, in this new paradigm that we call theory-guided machine learning. A major advantage of machine learning or theory-guided machine learning over traditional FE modeling is speed. And there is a lot of upfront efforts that you have to put in, but once trained, they are basically real-time with very minimum computational power needed to execute them. The other advantage that we have to look at is what's the difference of combining theory with virtual data, physical data, instead of relying on theory agnostic way of machine learning. First of all, we are ensuring physical consistency, especially outside of the training zone. I have to reemphasize that if a neural network model is trained with a specific set of data outside of the zone of those data, physically we cannot rely on the data. The response of the material might change drastically outside of that zone, and machine learning model has no way of knowing that has happened unless you bring in theory into that. The other advantage is that, as you could see, comparison of ML and TGML, you achieve higher accuracy with a smaller data set, which is usually the case we have. We always have small data sets in engineering applications. And at the end, I would like to acknowledge our sponsors and supports from our industrial partners, Boeing Company, Convergent Manufacturing Technologies, Torre, AFCorp, Composite Research Network at the University of British Columbia, and University of Washington. Thank you very much for your attention.